And of course, we always have to talk about the special cases. And these are special cases for linear equations. So the first thing that we're going to talk about is the number of solutions that a system can have. So up until this point, we've had and we've been calculating and working on practicing elimination and substitution of one solution. We've always had a solution, which we always wrote as a coordinate pair, x and y. And what that looked like on our graph, so we had our x and our y axis, was two linear lines. So we had a line going one way and another one going a slightly different way. Could be negative, could be two positives. But we had this point right here that was the one solution, that we solved for that one solution of that equation. Now, we could also have that solution if we had one going there and another one going right there. Notice that they're both positive slopes, but our solution right here is the y-intercept. So it could be the y-intercept, or it didn't have to be the y-intercept. It could be somewhere off the y-intercept. But what the important part was that they had different slopes. So that was the big thing, was that different slopes. And the first example I gave was one positive and one negative, and of course those are different because one's positive and one's negative, but if they could be positive and positive, but they're one steeper than the other, so that means that the change in y is a greater change than the change in x. Now, the next number of solutions you could have is no solutions. So the no solutions, so let's think about this. If we had two lines and they didn't, no meaning they didn't cross. So what two lines don't cross? So we know that those are parallel lines. So parallel lines will never cross. So if we had two equations that had two that made them parallel. Oh, so let's think about this. What makes them parallel? So that would be the same slope. So same slope for our parallel. Now we do have to think about what else. Well, the other thing is that they have different y-intercepts. So this y-intercept here for the bottom one is different than the one on the top. So that'll be same slope, different y-intercepts. Now our last one is what we call infinite slopes. Or not infinite slopes, infinite solutions. And it does have to do with slopes, but infinite solutions. And what we look for in these is, so we're going to have a line, a linear equation line, and I'll put my coordinate grid in. There's my y and my x. And when we have another one, I'll do it in light blue, we have this other line, the other equation will fall right onto the other one, which means that they are exactly the same equation. And if they're the same equation, they have the same slope and the same y-intercept. So notice how this is the no solution and infinite solutions both have the same slope, but the infinite solution has the same y-intercept and the no solutions have different y-intercepts. Now, I want to point out that notice I didn't write anything here. So a common confuser is that different slopes, different y-intercepts. And they kind of follows along with this one, which they extend their reasoning to that, but they're not true because remember we talked about that with one solution it could be different y-intercepts here, but it could be the same. They could cross at the y-intercept. Would it be, and it would be the same. So different or, and that's that key word of or, same y-intercept. So if you're going to talk about the y-intercept, you have to talk about it as different or the same. It could be one or the other. If you only said one of them, well, yeah, but not all of them would be true then. You have to name both different or the same. Notice the first time I didn't even say anything about it. I talked about it, but I didn't write it down. I only put the different slopes. But here, if I wrote it down, because I kind of wanted to write it down because I did with the other two, no solutions and infinite solutions, and but if I wanted to talk about it, I would have to say different or the same y-intercept. Or you could say something like, it doesn't matter if it's different or the same. Now, one more thing we need to talk about over here with infinite solutions is that they are, if we just say infinite solutions, we are in a two-dimensional plane. So when we say infinite solutions, we mean every single point on this graph. So it's like every single one. So I shaded everything, every point, which is not really what the solution is. It's the solution is infinite points on that line. So we should be saying infinite solutions on, and then I'm going to name that equation, y equals, and then we'll say that's probably what, 2 over, no, it's more like a 1 half, like the 2 over and 1 up. So it'd be positive slope about like 1 half, and then I'll give it a plus 2 as a y-intercept. So whatever that equation is, we want to include that into our infinite solutions because we don't want to say infinite solutions would be everything on the graph. It would be just the infinite solutions on that line. So now, how does that look for when we go into solving equations? So this is example 2. Well, the first example, but after the explanation. So we're going to use this by substitution. Now you may solve it a different way, but we're going to solve this one. Remember, you can solve it either way now, whichever way is the most efficient. But this one I want to do the solving. So if we have y equals 2x minus 5, oh, I can actually just look at this. It's in slope. Both are in slope-intercept form. So I have this same slope. So same slope and different y-intercepts, which means I can identify that this is a no solution, meaning that they are parallel. But we want to state there are no solutions where they will cross. They will never cross. We can't say that we can say that they're parallel, but when we talk about a system, that means that they are no solution. So when we calculate this, it's going to be a no solution. So when I solve this by substitution, like we were going to go to, I'm going to take that 2x plus 1, which is the y, and substitute it into the other equation where y is. So that means it's on the left-hand side, it's 2x plus 1 equals 2x minus 5. And we'll subtract 2x from both sides to get them together. That side it zeroes out, this side it zeroes out, and I'm left with 1 equals negative 5. And we know from past experience that that is not true, and that is why it is also a no solution. So when we have a calculation where it calculates both the x and the y are both eliminated when we substitute, that's when it comes into our special special cases. So this one is a no solution. Example number 3, we will solve by elimination. So our equation will be negative 2x plus y equals 3. Negative 4x plus 2y equals 6. So I'll notice, I kind of noticed that I could either double the top one. I think I will do that one. I like to double things. So I'm going to multiply the top by a negative 2 so that I can cancel out my y, and I have to also multiply the right-hand side. So now I'll rewrite it over here. So that would be positive 4x minus 2y equals negative 6. The bottom one stays the same, and I bet you can already figure out that things are weird or happening. So we'll add them, so that zeroes out, plus 0 equals 0. So we have 0 equals 0, and is that true or false? That is a true statement. So just like in the solving equations, this is infinite solutions, but different than solving equations. This is a system, remember? And when we write a system, our infinite solutions is on a coordinate pair. So on this coordinate pair means that these two lines are the same. So they'll be what? It's a positive slope of 2. And so that line and the other line will be on top of each other. But we want the infinite solutions on that line. We don't want all, when we say just infinite solutions, we're saying all the points on that coordinate grid. So everything, that was that shading that we did with all the points. But for this one, we only want it on the line. So you get to pick which equation. Now I did something to the top, so I'm going to pick the bottom one. And it doesn't matter which equation it is. It could be the top one or the bottom one that you choose, whichever one is that you like. But you want to write infinite solutions on, and that's the key word, on that equation. And that's how we write the infinite solution ones different. So now when we go down to a word problem, what we look for is the same kind of idea happens, but it's a little bit more complicated. So here we're going to talk about the perimeter of a trapezoid piece of land is 48 kilometers. So this one is 48 kilometers, the perimeter. The perimeter of the rectangular piece is 104 kilometers, or 144 kilometers. We're going to write and solve a system of linear equations to find our x and y values for that system. So to find perimeter, I'm going to add all those up. So to add them up, I'm just going to first write them out. 2x plus 4x plus 6y plus 6y equals 48. My second equation is 9x plus 9x plus 18x, or y, plus 18y equals 144. So now it's looking very complicated, but I can simplify it by combining like terms. So I'm going to combine like terms before I do any of my solving. So 6x plus 12y equals 48, and 18x plus 36y equals 144. Now, it would be kind of nice to get everything a little bit smaller, but you know what? I like that 6 to be an 18. I could just take and multiply that by a -3, which means that on my right-hand side, I also have to multiply by a -3. So, -18, and I'll do it in a different color so that you can kind of see -18 and minus 36y equals 24, 12, 144, and it will be negative. So when I add them, my y's are lined up, my x's, they're on the same side, so that would be 0 plus 0 equals 0. So right there, that tells me it's a true statement, and that means it is an infinite solutions. Now remember, we have to put on one of those equations. Now it doesn't matter which equation you use. You can use this big one up here, the second big one. I like the 6x one. So on the 6x plus 12y equals 48. And it could be any of those. Could be the 18 one, the 18x one, any of those, but you do have to have one of those equations as part of your infinite solutions on that 6x plus 12y equals 48.